Okay, dear students, so this is our 1 second. So this is our lecture number 2, electromagnetic induction. Electromagnetic induction. Electromagnetic induction. Lecture number 02. So that's our lecture number 02 here. So let's solve the question. The things which we have studied in the previous session, we'll solve the questions related to that. Question. This is the question now here. A conducting circular loop is placed in a uniform magnetic field 0.04 Tesla with its plane perpendicular to the magnetic field. The radius of the loop starts shrinking at 2 millimeter per second. The induced EMF in the loop the radius is when the radius is 2 centimeters will be. So this question was asked in 2009. Please note down this question, then we'll solve it. Okay, let's understand this question. Solution. So we are given here as conducting circular loop is placed in uniform magnetic field. So we are having here a conducting circular loop, okay, and it's placed in a uniform magnetic field. Field given to us is as equals to 0.04 T, okay. And next it says with its plane perpendicular to the magnetic field, the radius of the loop starts shrinking. So basically we have dr by dt, but it's not expanding. I mean, suppose this is a loop, this is the radius of the loop, this is the radius of the loop, okay. So with time, the radius can expand, can shrink. If it expands, the value will be positive. If it shrinks, the value will be negative. But what here we will consider is that it will take it as positive. Actually, we'll take the magnitude. It is negative by the way because it's shrinking. So we'll directly write the value. We'll directly write the value here. dr by dt is equals to shrinking. It is 2 millimeter per second. So we'll say it is as 2 milli means 10 minus 3 meter per second. Okay. The induced EMF in the loop when the radius is 2 centimeter. They're asking us the induced EMF in the loop when the radius is 2 centimeter. Induced EMF. So we know that EMF is given as d phi by dt by magnitude. I'm not taking signs here. It's from the Lenz law. We already have deduced this. Lenz law. This was from the Lenz law. Okay. Now it says that d phi by dt. So basically, they're asking us EMF induced at a particular radius, which is equals to 2 centimeter. Centi here is basically 10 minus 2 meter. Okay. So this was the thing here. Now let's proceed next. They're asking us the induced EMF. We know that the EMF is given as by this. But for a loop, we also know that the flux is basically B dot A. Here, if we see properly in this question, the magnetic field is basically constant given. So we'll get B outside and then we'll be having dA by dt. Again, since it's a circular loop here, so we have the area for the circular loop as pi r square. And when we'll solve it, when we'll put the value inside, pi will come out. This will be dr square by dt. When we will differentiate it, we'll get the answer as b pi. This is 2r, and that will be dr by dt. So here we are having 2 pi r b. dr by dt here given to us as, we have already seen it, that is 2 into 10 minus 2. So we have dr by dt is 2 into 10 minus 2. Okay. We have 4 pi rb into 10 minus 2. Now we can put the values. 4 pi radius we are given as at the radius. It's been asked to us that we need to find at a particular radius, say 2 centimeter. Okay. Centi we know already, it's 2 minus t. 2 minus 10 is to the power minus 2. And magnetic field. Magnetic field here we given as 0 0.040. Okay. And then this is 10 minus 2. So we'll check it out here as, this is 8 pi, this is 4 upon 100, and this is 8 pi, this is 4 upon 100, this is 10 minus 4. So here we have pi upon 100, 10 minus 4. So here if we see, we are having 32 pi, and this is 10 minus 2. This, the value will be ultimately, if you want to solve it, actually this is not 10 minus 2. If we solve it properly, you'll get 10 minus 6. We know that 10 minus 6 is basically micro. So this is 32 pi, but 4, 5, 6. Yeah, it's fine. Let me check the values here. 10 minus 2, this is 4 here. Maybe I missed some value. This is 10 minus 4, 5, 6. Okay, 2 upon 100. Yeah, we didn't converted this actually. So this goes as 3.2 micro. Okay, volt. This is the EMF induced. So you can note this solution. I have minimized this for you. Please note it down. Now we'll solve. We'll go through a theory of induced charge. Now the questions can also be asked on the topic that is induced charge. Okay. So this was a topic that is induced charge here. So we know that EMF is equals to d phi by dt. This was by the Lenz law. We already have seen this. By the Lenz law, we've already seen this. Now we know that current into resistance is EMF. Okay. Now, so we need to find the induced current. So this is the induced EMF basically. This was the induced EMF. So via this we need to find the induced current. Via this we need to find the induced current. So induced current will be 1 upon R d phi by dt. Okay. So we also know that current is equals to dq by dt. So dq by dt is equals to 1 upon R d phi by dt. Okay. So here if we see, can cut off this dt dt, we have dq is equals to d phi r. When we integrate this, we'll get the value as q del phi by r. It does not depend upon time. So remember this, okay? This formula is very much important. Please note it down. So whenever you need to find induced charge, you'll use this formula, okay? So step by step we'll progress towards the next. So we have already seen the theory related to induced charge. Now we'll see a numerical based on this, okay? Numeric. So we have here the magnetic flux. We have the magnetic flux through a circuit of resistance R. Basically, it changes by an amount. Basically, it changes by an amount del phi in a time del t. Then the total quantity of electric charge Q passes any point in the circuit during time delta t is represented by. So we need to find the representation of this. This question was given in 2004. Okay, we solve this. I think in this question, it's not required for you to solve anything, isn't it? Because we already know that we have already derived it. Let us derive it again. We know that we know this thing EMF induces d phi by dt. Now this behaves as a volt. So as per the Ohm's law, it's I into resistance d phi by dt. Okay. Now current we have as d phi by dt into 1 upon r. Okay, fine. So current we already know, again it is dq by dt. So here if we see dq d phi by r, so we get it as q del phi by r. This was change in flux. This is resistance. Okay. Now we'll solve the next question. So we have a representation here. This is our required representation. So yes, this is the required representation. A coil of resistance 10 ohm, the induced current developed by changing. I'm writing here the question for you students. By changing magnetic flux through it. You need to find the magnitude. You need to find the magnitude of change in flux through the coil in Weber. And the diagram which is connected with this question is this. We have a graph. We have a graph between, this is 4, this is 0.1, this is I ampere, then this is 0, and that's time in second. Okay. So this is 2012. Yes, that's the year. So please solve this question. It's present in front of you on the screen. So now we'll solve this question. Okay. Let's use our equation. As per, let us relate the solution here. We know our equation was what? Q is equals to del phi, this change in flux by resistance. And if you see this graph is between current and time. You know this thing that current is equals to dq by dt. And if we integrate current with time, we get here as dq. Okay. Here we have as dq here. So this basically gives us that area under current time graph. Okay, area under current time graph. So we see here we have half into 0.1. You can check from this that this is basically a right angle triangle. Half into base into height. So that's the area, that is 2 into 0.1. That will be equals to 0.2. Okay. So that's area, and this basically gives you the charge here. Okay. So we have Q is equals to, Q is given to us as 0.2. There's a charge given to us. Q is equals to 0.2 net charge we're having here, and whereas the magnitude of change in flux. So Q we have, as per the formula, we have change in flux upon resistance. From this we can get the change in flux as 0.2 into the resistance value. So you know this thing, the resistance value is given as 10 ohm. So when you solve this, we'll get a drop here of 10, and then this. So this is 2. So that is basically 2 Weber change in flux, or you can call it as Tesla meter square, as per the formula B dot A, simple formula. Okay, let's move next. Please note this solution. I minimized it. Please note it down fast. Okay, I hope you have noted down. Let's move next question. So here if we see, we are having a solenoid basically. So directly I'm drawing the question. I'll explain it and then you have to solve it. Okay. So that's a solenoid here. And this solenoid is having the diameter, basically diameter. This solenoid is having the diameter basically as 0.1 meter. Okay. That's the diameter of the solenoid. And we have here the number of turns per unit length given us as 2 into 10 to 4 turns per meter. Okay. And at the center of the solenoid, we have a coil of 100 turns and radius 0.01 meter. The number of turns basically we have here as 100 turns. And radius is as 0.01 meter. Okay. The current in the solenoid increases from 0 to 4 ampere. And then the resistance is given to us as 10 pi square ohm. We need to find the total charge flow. We need to find the total charge flow. Okay, so that's 2017. Try to solve this question. Okay, I will solve this for you. Let me narrate the question for you. So you are having a long solenoid whose diameter is given to you as 0.1 meter. So if you mark the diameter here, it's something like this. So that's 0.1 meter. It is having these many number of turns per unit meter. At the center of the solenoid, they are saying a coil of 100 turns and radius 0.01 placed with the axis coinciding with the solenoid axis. Now here at the center, there's a coil which is having basically number of turns as 100 and radius is smaller. I mean, it will be small then, and axis is parallel axis to the solenoid axis. The current in the solenoid basically increases from, so current is basically increasing from 0 to, we have 4 ampere, and if the resistance is this much, total charge flowing is being asked from you. The easy question, okay? First of all, we know this thing, the magnetic field lines will be passing like this, so flux will be generated, okay? And if we see here, flux is equals to NB dot A. Now we have NBA cos theta. We have phi as NBA. Remember the axis is parallel. So for the parallel axis, we have the angle as 0 degree. So cos 0 goes 1. So we are having here as theta 0 degree cos 0 1. Okay. NBA. So if you see here, B and A, we know that at the center of the solenoid, the magnetic field here is mu n I. Mu n I. So, and the area, if we see, area is pi. If we see here, area is pi r square. Okay, area is pi r square del phi. So flux change here. We need to find this out. Flux change basically. So the flux change will be, we'll put here delta because there is a change here. Same delta I put here, same delta on the RHS. Okay. So now the flux change will be is equals to N mu n. Current can change. Rest of the things if you see here will be same. And we know this thing Q is equals to del phi by R. So let us solve this for that. So when we'll divide with R, we'll be having here Q as del phi by R and mu n del I by R square by R. Okay. So that was a thing we have solved already. We can also finally manipulate it. If we put the values we need to find. So after putting the values, the answer which you will get it as, the answer will be finally this. So charge ultimately flowing will be 32 into 10 minus 6 coulomb. 10 minus 6, we know this value is 32 microcoulomb. That's the charge. Okay. So all the values are given to you. You have capital N value, radius value, this R value. You have number of turns per unit length. You have current increment here. Okay. All these things you can use yourself. Okay, please note it down. Then we'll move next. Okay, I hope you have noted it down. In the next session, we will go through proper understanding of the Lenz's law. Okay, till then, practice these questions again. You will able to find whenever we practice more and more questions, we are able to understand the things in much better way. Okay, so now we can leave here.